Factoring is polynomial. Of course, we're still testing and polishing the results. The status of our project. Everything in this video and the code is a mess. We are now learning how to describe the algorithm, and this is our first attempt to describe some of the ideas herein. Polishing, testing, and tweaking will probably take another year. Garbage can packing is working with 26 garbage cans or 64 decisions, but factoring needs testing on larger computers. We can factor 2-bit products with 32 decisions, but 4-bit products with 128 decisions is too large for our computer. We intend this video as a heads up that change is coming. Ignore our previous videos. There were many problems. Most were small with simple workarounds, but they lurked everywhere. And our intuitions went seriously awry. Small butterflies can easily be drawn by hand, and they work like expected. But large butterflies of size 16 or larger are too big to be drawn out by hand, and they simply behave differently. Our work is based on the Hadamard population equation, which we proved in the SOME2 2 years ago. The video is linked below. And the consistency algorithm that we will work on today works like this. Given a number of bits b, a set of constraints c, and a number of truths t, find a vector v that has b bits that satisfies all of the constraints in c and has t truths. We're going to start with an easier problem, extracting valid binary vectors from pure Hadamard butterflies. We're going to ignore partial sums for now. Don't mix vectors. Here's the Hadamard butterfly for the vector 0, 1, 0, 1. The top row is the binary vector input. Subsequent rows contain the intermediate and final computations of the Hadamard transform. And here is the Hadamard butterfly for the vector 1, 0, 0, 1. The top row is the binary input vector, and the remaining rows are the Hadamard computation. Here is the butterfly for both vectors put together. We simply juxtapose the values in each node. Consider making a Hadamard butterfly for the vector 1, 1, 0, 1, which combines 2 bits from each of the butterflies above. None of the values 3, -1, 1, or 1 were contained in the butterfly for either of the other vectors. Consider making a butterfly with the Hadamard vector 2, 0, 0, 0, which contains 2 values from each Hadamard vector. In this case, the root nodes would each be 1/2, 1/2, 1/2, 1/2, which is impossible because binary Hadamard vectors can only contain integers. Population. This is the Hadamard butterfly for either of these 2 vectors. The nodes marked in black are the population nodes for this butterfly. And storing the Hadamard and population value in each node looks like this. The population for any root node is equal to the Hadamard value of that root node. The population of any child node is equal to the population of the left parent plus the population of the right parent. Spine. This is the Hadamard butterfly for the 2 vectors 0, 1, 0, 1 and 1, 0, 0, 1. The nodes marked in black are the spine tree for this butterfly. Putting both the Hadamard and the spine together for each value in the butterfly looks like this. The population of each leaf node is equal to the Hadamard value of each leaf node. The population of each parent node is equal to the sum of the population of the left child node and the population of the right child node. Solution butterflies combine the Hadamard value, the population value, and the spine value. Here we have the solution triples for the butterfly that combines the vectors 0, 1, 0, 1 and 1, 0, 0, 1. Solution facts versus solution deltas. Solution facts are simply the Hadamard value, the population value, and the spine value together. A solution delta defines the relationship between 4 facts, between 2 child solution facts and 2 parent solution facts. Specifically, it defines the flow of information from the child facts to the parent facts, or vice versa. So we're going to store the left and right child Hadamards, the left and right parent populations, and the left and right child spine values. The left and right parent Hadamards can be computed as shown below. The child population and the parent spine can be computed as shown below. The complexity is that there are approximately n cubed possible solution facts in each node, and there are approximately O(n) to the sixth solution deltas in each box. We need to distinguish facts and deltas. Facts reside in the nodes and are triples. Deltas reside in the boxes, and they are relationships between the different triples. This shows that the child Hadamards of 1 and -1 can be combined to create the parent Hadamards of 0 and 1. The parent populations of 2 and 3 can be combined to create the child populations of 5 and 5. The child spine values of 1 and 3 can be combined to create the parent spine values of 2 and 2. We need deltas because facts do not always combine with all other facts. For example, on the right-hand side, the triples 0, 2, 2, 1, 3, 2, 1, 5, 1, and -1, 5, 3 are parts of various other solution deltas, but those two child values do not create those two parent values in this situation. Domains. The default domains for Hadamard values are shown here. There's really two kinds of domains. The ones in black are the population domains, and they range from 0 to 2 to the n, where n is the tier. And the other domains range from -2 to the n minus 1 up to +2 to the n minus 1, where n is the tier. The population domains are, of course, pretty much all the same, or 0 to 2 to the tier. And the default spine domains, it turns out, are equal to the default Hadamard domains. However, the population and spine domains come from someplace else. If we label the actual domains A to A prime, B to B prime, C to C prime, and so on for each of the nodes, and these are the Hadamard domains, the population and spine domains refer to the Hadamard domains of other nodes. Here the arrows point out how population domains map onto Hadamard domains, and here the arrows point out how spine domains map onto Hadamard domains. And here is the code that maps population and spine domains onto Hadamard domains. We found it very useful to define a new kind of Hadamard domain called a binary group domain. Basically, we're going to have each value that we care about expressed by two adjacent decisions, A and not A, B and not B, C and not C, and so on. The values are redundant. However, this organization gives us a bunch of benefits. First off, we note that the Hadamard values down below in half the cells are constants. Because one of each pair must be 1, we know that every other node must be a 1. And then the row below it, there must be a 2 and a 0 and a 2 and a 0, and so on. The population of the group binary is always 1 in the second tier, and is always 2 in the third tier, and is always 4 in the next tier, and so on. And the spine domains are exactly like the Hadamard domains. The trade-offs are this. Using this binary group requires larger butterflies. Butterflies need to have 2n terms and m+1 tiers, so the butterflies are bigger. However, for non-root nodes, there is exactly one population value, which means that solution facts are actually O(n) squared values, not O(n) cubed, and solution deltas have O(n) to the fourth values, not O(n) to the sixth. Furthermore, half of the non-root nodes have exactly one Hadamard value. The other advantage is this simplifies the simultaneous logic between tiers. Simultaneous. Every value in the root vector must link to the same leaf vector, and everything in the leaf vector must link to the same root vector, and we have to do both at the same time. Whatever values we choose in the leaf vector, they all must share a common root vector. These two values, whatever they are, must produce the same spine value. These two values must produce the same spine value, and these two values must produce the same spine value. At the next level up, there are only two different spine values amongst these 4 nodes, and whatever values they are, all 4 parents must share the same spine value. Likewise, in the second to the bottom tier, there are only 2 spine values, and whatever spine values they are, they must all produce the same spine value. And here, There are only two green values, and they must all produce the same spine value at the root vector. So that's what this picture is about. We call bottom-up canonical Hadamard spine values. Each spine value in the leaf tier may differ. All spines in the root tier must be the same. And in general, the left and right children and parent spine values differ. Likewise, every node must share a common root vector. The two root population values, whatever they are, must produce the same population value at the next level down. These two population values must produce the same population down, and so on and so on. At the next level down, there are only two population values because they have already been mixed, and so these four values can only produce one population value at the next level down, and these four nodes can only produce one population value at the next level down. And likewise, there are only two population values in the green row, and they must produce the same yellow population value at the bottom. So that's what this picture means. We call canonical top-down Hadamard's population values. Each population in the root tier may differ, although all populations in the leaf tier must be the same. In general, the left parent, right parent, and child populations may differ. However, using the binary group structure, the domains of population values may actually be very limited. Simultaneousness. The problem with simultaneousness is this. The population deltas and the spine deltas for each node are not independent of each other. Whatever population delta is chosen in each row must match all of the spine deltas chosen in the columns. So the population deltas and the spine deltas are shared in a complex web of connections. We know of two ways to solve the problem. One is to start from all possible spine vectors and then verify that they match population vectors. Or the other one is to do it incrementally using dynamic programming, which, alas, is kind of tricky. Considering whole vectors is simple, but there are a sub-exponential number of them. The alternative is to store incremental markers, which is tricky because it requires dynamic programming, but it is polynomial. To compute simultaneous, the gray dots represent various solution deltas which correspond to specific population deltas and spine deltas. In the root node, all of these deltas are valid. In the top row, when we move to the right, all we require is that each node matches a corresponding population delta in the previous node. And moving down to the left, we require that each delta has a corresponding spine delta in the previous node. For all nodes below this, we require that there must be a parent node which produces a spine value and a population value that each then correspond to the current node down below. If there is, then this node is valid. Following these four deductions throughout all of the nodes in the tier will produce a graph that contains all valid combinations of population deltas and spine deltas. And then by working in reverse order from the bottom back up to the top, one can winnow out all of the bad values. The problem with this model of simultaneous is that it ignores the tier-to-tier constraints. Binary groups handle this implicitly, but we do not yet fully understand it for default domains. Linking butterflies. Equation butterflies look like this: Hadamard value, population value, spine value, and partial sum. To merge the equation butterflies, the solution facts need to be projected away from the partial sums, because the partial sums differ for every equation butterfly. But projecting before merging always failed for larger butterflies. Eventually we realized that projecting after merging does work. So we use linking butterflies. We build one linking butterfly for every pair of equation butterflies and then project away the partial sums after we create the linking butterfly. The linking butterflies express the interferences between each pair of equation butterflies. Linking butterfly facts look something like this. They have a Hadamard value, a population value, a spine value. The first partial sum comes from the first equation butterfly, and the second partial sum comes from the second equation butterfly. Equation butterfly deltas look similar. the algorithm. There are three main functions. The constructor builds the data structure. It creates a property butterfly, a solution butterfly, then it creates one equation butterfly for each constraint, and finally it builds one linking butterfly for each pair of equation butterflies. Note that we do not need linking butterflies for an equation butterfly with itself. Also note that symmetric links are redundant. The second function is merge bottom up. The first step is to intersect the shared state at the leaf nodes. So we intersect all linking butterflies to their shared state, and then intersect the shared state back to the linking butterflies. Then for each box tier in a bottom-up manner, we first ring once bottom up, which moves the child facts into the box deltas. Then we intersect the shared state within each linking butterfly. Then we intersect the linking butterflies to get the spine deltas. Then we go backwards. We intersect the common spine deltas back into the linking butterflies. Then we intersect the spine deltas among all butterflies back into each butterfly, and then we intersect the shared state within each butterfly back into each linking butterfly. And finally, we ring once bottom up to move the constraints from the deltas into the parent nodes. Extract top-down is actually very similar. It just goes in a top-down direction. There's only two differences. In the middle, after we have intersected the spine deltas, we choose a spine delta for each box. And finally, after processing each tier, we ring all the butterflies to get rid of extraneous facts that are no longer consistent with the chosen spine deltas. Finally, the extract solution simply picks up whatever Hadamard values are in the leaf nodes of any butterfly. Note that in the above code, the ALN-ALB refers to processing all leaf nodes in all linking butterflies. ATB-ALB refers to processing all tier boxes in all linking butterflies. A note on the complexity: there are approximately n to the fourth deltas per equation box. There are n log n boxes per equation butterfly. There are n to the 8 possible linking deltas. There are n log n linking boxes per butterfly. There are probably n squared linking butterflies per problem. Constraints per problem are usually between ON and ON squared, and the iterations per ring are O log n. So the complexity of the algorithm is probably much worse than n to the 20th. So this algorithm is impractical in every possible sense. However, if the algorithm turns out to have merit, then factoring is no longer trapdoor.